Now that we've done double integrals, we're going to find that triple integrals are pretty much more of the same thing. So here, we use a triple integral sign and integrate that over a given volume V. We have a function of 3 variables, and we now have a volume element instead of a length element for a one-dimensional integral, an area element for a two-dimensional integral. Now we have a volume element for a three-dimensional integral. And the most obvious choice for that volume element is the product of length, width, and height. As before, the ordering matters to the way you actually do the integrals. Now there are actually 6 orderings for 3 objects. So a very large number of possibilities. The easiest case is when all the limits of integration are constants. So let's write this in the order dz, dy, dx, for example. So z might go between c1 and c2. Y might go between b1 and b2. And then x between a1 and a2. So in this case, the volume that we're integrating over, we could write that as the product, if you like, of 3 intervals. Now, if we change the order of x, y, and z in the integral, all we'd have to do is just change around the order in which we do those limits of integration. Pretty straightforward, just like we had to do when we first did double integrals over rectangles. Where things get trickier is when the limits of integration are not constant. Here we're going to look at a triple integral for the region bounded by this plane and the 3 coordinate planes. So we write down our integral, and we're doing it with respect to z, then y, then x. Remember, we still go from the inside out. Okay, so here's a plot of the 4 planes that bound our region. This is the x plus y plus z equals 1 plane. Okay, and then the 3 solid colors are the 3 coordinate planes. As usual, z is oriented upwards, y is oriented along the page or along the screen, and x is oriented more or less coming out at you. So we can spin this around and take a look at it. You can kind of see that inside the area, the volume that we're integrating over is a tetrahedron, okay, 4-sided solid. And if we integrate, as we said before, if we're going to integrate with respect to z first, then that means we imagine lines going up parallel to the z-axis. Okay, so when they intersect this volume, they intersect it at the green plane going in, and then at this semi-transparent plane coming out. Right? So as you come up, you intersect it at the green plane, that's z equals 0, and then you intersect it at whatever z coordinate is on this plane. Well, when you're on this plane, which is the transparent one, then z is equal to 1 minus y minus x. And we said we started from z equals 0. Okay, so those are the limits on z. Now, if we want to look at the limits that remain in x and y, one thing we can do is look down along the z-axis. Oops. Okay, so now we're just looking at it from the top down. Okay, here's y equals 0, here's x equals 0. All right, and As you can see, imagine now that those lines are coming straight up at you when we did z. All right, some of them miss over here. They miss the whole solid. Over here, they hit the solid volume that we're integrating over. So they hit over this triangular patch here. Okay, so what is that patch? Well, it's bounded by x equals 0, y equals 0, and this line, which is x plus y equals 1. Now, how do I know it's x plus y equals 1 without even doing any algebra? Well, remember, when it intersects that edge of the triangle, that's when z is equal to 0. When z is equal to 0 along that top plane, we just have x plus y equals 1. Okay, so now let's do the y direction next. So we have a vertical line intersecting through this region. So y goes from 0 down here to whatever it is on this line here, which is 1 minus x. So y goes from 0 to 1 minus x. So after we've painted this whole thing in vertical lines, okay, where do they have to go from? They have to go from x equals 0 to x equals 1. And that's the setup of the integral for this region.